For more than half a century, one question has haunted astronomers more than any other. Not whether planets exist elsewhere in the galaxy, but whether they exist right next door. Alpha Centauri, the closest sun-like star system to Earth, has always felt like the universe's biggest tease. Close enough to imagine reaching, similar enough to feel familiar, and yet stubbornly silent. Every attempt to find planets there failed. The stars were too bright, the system too chaotic, and the technology was never quite enough. Then the James Webb Space Telescope did something it was never meant to do. It turned its most sensitive instruments toward one of the brightest stellar systems in the sky and pushed itself beyond its original limits. What it saw did not bring clarity. It brought unease. A planet appeared beside Alpha Centauri A and then vanished. A detection strong enough to pass every statistical test was followed by silence where certainty should have been. Orbital paths that should not exist. Conditions that challenge how planets form, how they survive, and how close potentially habitable environments might really be to Earth. This is not a story about a single observation. It is about proximity becoming a problem instead of an advantage, technology being forced past its comfort zone, a planet that refuses to behave like a planet, and the uncomfortable realization that our closest stellar neighbor may be far stranger than we ever feared. What James Webb saw in Alpha Centauri did not answer our oldest question. It made it more unsettling than ever. When James Webb observed Alpha Centauri A in August 2024, astronomers were not expecting a clean result. The target itself violated nearly every rule of exoplanet hunting. The star's brightness overwhelmed detectors. Its binary companion flooded the field with contamination, and its rapid motion across the sky complicated precise pointing. Yet, after hours of observation and months of custom data processing, something emerged from the glare. A faint point of light appeared roughly 2 astronomical units from the star. It was not marginal. It was not ambiguous. The signal reached a statistical significance of 5.5 sigma, strong enough that random noise was essentially ruled out. Against all expectations, a planet candidate had revealed itself beside the closest sun-like star to Earth. The team did not celebrate. They interrogated the detection. Every known source of error was tested and retested. Background stars were eliminated using Gaia catalogs. Distant galaxies were ruled out through spectral behavior. Moving solar system objects were excluded by tracking their motion during the observation itself. Instrumental artifacts were challenged through injection and recovery tests designed to expose false positives. The signal survived all of it. Split data analysis showed the object appearing consistently across independent subsets of the same observation. Whatever S1 was, it behaved like a real astrophysical object bound to Alpha Centauri. For the first time, the idea of a planet around our nearest solar twin moved from speculation into measurable evidence. Confirmation should have been straightforward. Planets move. Their positions change predictably over time. Follow-up observations were scheduled for February and April 2025, using the same techniques that revealed S1 in the first place. The telescope performed flawlessly. The data were processed with the same pipelines, the same reference stars, the same corrections, and yet the planet was gone. The region where S1 had shown clearly in August showed nothing but noise. No trace, no marginal signal, just absence. A planet that passed every test had apparently disappeared. The result stunned the team. Not because they contradicted expectations, but because planets do not behave this way. Gravity does not allow objects to simply vanish. 3 explanations remained. The first was deeply uncomfortable, an extraordinarily rare statistical fluke. The second involved an unknown background source that somehow evaded every catalog and test. The third was the most unsettling and the most intriguing. S1 could be real, but moving along an eccentric, inclined orbit that carried it into regions where JWST's coronagraph becomes effectively blind. Orbital simulations showed that more than half of all stable orbits consistent with the August detection would naturally produce non-detections in both February and April. In other words, disappearance did not disprove existence. It fitted. The planet did not vanish. It moved into darkness. Alpha Centauri has always occupied a special place in astronomy. Not because it is exotic or distant, but because it is familiar and close. At just 4.37 light-years away, it is the nearest star system to the Sun, and Alpha Centauri A in particular is almost a mirror of our own star in mass, temperature, and age. For decades, astronomers assumed that if planets were common anywhere, they would surely be found here. This proximity created confidence, even optimism. Unlike distant exoplanet systems that push instruments to their limits, Alpha Centauri felt approachable, almost cooperative. Yet year after year, searches came up empty. Radial velocity measurements failed to reveal clear signals. Transit searches found nothing reliable. Each null result quietly chipped away at the assumption that closeness makes discovery easy, turning Alpha Centauri from a promising target into an unresolved problem. The document makes clear why Alpha Centauri has resisted detection for so long. Its very brightness, the quality that makes it visible to the naked eye, becomes a liability for precision instruments. The star overwhelms detectors, saturates sensors, and floods the field with scattered light. On top of that, Alpha Centauri is not alone. Alpha Centauri A and B orbit each other in a tight binary system, constantly shifting positions and contaminating observations with overlapping glare. The star's rapid proper motion across the sky further complicates long-term monitoring. Instead of a stable target, astronomers are dealing with a moving, blinding, gravitationally complex system. The closer they look, the more the star fights back, turning proximity into a technical obstacle rather than an advantage.